Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I am super happy to have Riley McGlasson with us today. Hey, Riley.
Hi, Frank. Thanks for having me.
Sure. Well, thanks for agreeing to talk about your very lovely article. And Riley, where are you at? What's your geolocation?
Thank you. Yeah, so I am currently located at Purdue University, where I'm a second-year PhD student. So I'm in Indiana.
Very cool. It's April 12th as we do this. Do we have 6 feet of corn yet in Indiana, or are we getting there?
Not quite 6 feet of corn, but also not 6 feet of snow. So the happy in between.
Good. So spring has hit in the Midwest. Very nice.
Yes.
At least for right now. Who knows? Next week could be quite different.
Yeah, that's a dangerous statement to make.
Indeed. So yeah. So you're almost done. Have you done your quals? Are you all but dissertation at this point?
So at Purdue, we do a quals and a preliminary exam. And so I am post-quals, but pre-prelims. Okay. So I'm not a PhD candidate yet. That'll hopefully come next fall.
You will do awesome. It will be. And so I see you must be in an office in Purdue. So is Purdue operating full bore at this point?
Pretty much, yeah. We're getting pretty close to back to, I guess, how it was. You know, never will be quite the same. But yeah, it's weird. It's weird, but we're back mostly in person at this point.
Cool, very cool. And Riley, what do you like to do for research?
Yeah, so interesting enough, this paper was the research for this paper was conducted under an RAU while I was in undergrad at Palliser College. And I was studying astronomy there. Now I am a planetary science student in a Department of Earth, Atmospheric and Planetary Sciences. So coming more at planetary sciences from a geology lens now than an astrophysics lens. Mm-hmm. But actually I still do planetary radar, which is great.
Awesome.
And I would say that this RAU experience in this project was pretty instrumental in helping me decide to pursue this PhD in planetary radar. And actually, funnily enough, my PhD advisor, Ali Bramson, is also a former Arecibo RAU student.
Wow, very cool.
Yeah, so fun connections all around.
Very nice. And that, speaking of, is going to bring us to this very lovely Planetary Science Journal article. Open access, people, you can go get it. Radar and light curve observations in a physical model of potentially hazardous asteroid, 1981 Midas. And Riley, take us away.
Thank you. Yeah, so this paper, we present a three-dimensional shape model of Midas, which is a potentially hazardous near-Earth asteroid, which just means that it's fairly large and it has an orbit that brings it fairly close to Earth. Although I should preface this as saying there's no reason for me to say that we need to be concerned about this asteroid.
There you go. Public safety announcement there. There we go.
Yes. Yeah, no need for panic. Midas isn't going to destroy us.
Right.
But yeah, so looking at this asteroid, we looked at it with both planetary radar observations from Arecibo and also from the Goldstone telescope. And then we also have light curves dating all the way back to 1987. So if we start with our radar observations, all of our radar observations come from March 2018, which we were able to observe it over 6 nights. So we got some pretty good coverage overall. If you scroll down to table 1, you'll be able to see a summary of all of our radar observations. So you can see that Goldstone was able to catch it at the first part of when it was visible in our skies, but then Arecibo caught the back chunk of that. And we're able to get a combination of continuous wave spectra as well as delayed Doppler images. And delayed Doppler images are going to be more useful typically in being able to get a better constraint on the asteroid's actual shape.
Okay.
Yeah, and especially with Midas, which we've seen is a more complicated shaped asteroid, and we'll see this in some following images. But because it has some more nooks and crannies and interesting things going on, being able to see those more detailed, higher resolution delay Doppler images was really helpful.
Cool.
So actually, if you scroll down to figure 1, we can see some of
Let's take a look
those.
at some of these. There we go. Let's blow that up a wee bit. There we go. Okay.
Yeah, so these are delay Doppler images. And if you've never seen a delay Doppler image before, you might be a little confused because they're a little weird. This isn't just like we normally think of telescopes where you just take in all of the light coming in. With radar, we are sending a signal to the asteroid and measuring what comes back in delayed Doppler space. So increasing across the left axis or across the horizontal axis is the Doppler shift.
Okay.
And then going from increasing from top to bottom is the delay, or the time that it takes for the signal to return to the telescope.
Okay.
So if we take like a spinning water bottle asteroid here, and we bounce a signal off of it, you can see that one side is going to be red shifted and one side is going to be blue shifted, rather depending on whether it hits the side that's coming towards us or the side that's rotating away from us.
Cool.
And then similarly, where we get the change in delay, if we hit this equator part of the asteroid that's closest to us, that signal is going to come back to us faster than something like up here at the top, where it's going to be further away. So yeah, so you can kind of think about it as almost a cross section of the asteroid. So this leading edge that we see in a lot of these images is usually approximately at the equator, which creates some issues with radar. You get this north-south ambiguity where, since you're only seeing how far things are away, you don't know if that's above the equator or below the equator.
Okay.
And because of that, you need a lot of observations and a lot of radar observations to be able to kind of disentangle this ambiguity, which luckily we have for Midas, which makes it an excellent candidate for shape modeling.
Nice. Very good.
And then
shape modeling, shape software.
Yes. So we also, I should mention, we use Lightcurve observations as well. This we don't get as much information about the shape. You can do some shape modeling with Lightcurves, but you end up getting convex hull models. So anytime you have any indentations, which, since we found Midas is a contact binary, there is that neck that goes down, which we wouldn't be able to see if we just have Lightcurves.
Okay.
But having a wide variety of Lightcurves ranging from 1987 to 2018, we were able to see Midas at a wide range of viewing geometries, which helps us better constrain which direction, for example, the rotational axis is pointing, which can be pretty hard to figure out with just radar observations.
Great baseline.
Yeah. So if we want to get into the meat of the shape modeling, we use this software called Shape, which was designed specifically for asteroid shape modeling, and it does a pretty good job of it, considering that it's a pretty hard problem to solve. Asteroid shape modeling has many free parameters. I think for Midas, there is over 1,500 free parameters in this model, which is quite a lot to work with. Every vertex that makes up this three-dimensional mesh, each coordinate of each vertex is its own free parameter, as well as different like scattering parameters and spin rates and all of that. So there's, I would say there's between 15 and 1,800 free parameters in this model. I can't remember the number off the top of my head, but it was
it's a border
around there.
Yeah.
Wow. And so this shape software is an iterative model, so it makes small changes to each of the parameters that we're deciding to work with in each modeling run, which means that if you're going to make a lot of big changes, it's going to take a really long time. And in each of these modeling runs, where you're changing the free parameters a little tiny bit, the goal is to minimize that squared residual.
Mhm.
And so when we do that, then that means we're fitting the data better. But especially if we're trying to traverse a large parameter space, you can get stuck in local chi-square maxima or local chi-squared minima. So you might not actually be able to get to that true best model just with the modeling software alone, which requires us to do some manual tinkering by hand. And actually, in this model of Midas, one of our goals was to kind of test if there are ways that we can speed up these big jumps that we make in the modeling.
So I have a question. How long does it take to do one shape model? Give me some 1800 vector parameter run. How long does it take to run? Is that a 1 minute? Is it a 2 day? Is it a week?
So we were able to run it on like 32 cores of a server, which sped up the time significantly.
Sure.
9 years before I did this, when my current advisor was working on a similar shape modeling problem, one run would take a couple months, where now one run would take closer to between 8 hours and a day, depending on how many parameters we were allowing to vary.
Thank you. That's useful. Thank you.
Yeah, so it's gotten a lot better over time, but it's just a tricky problem to solve, so it's going to take a lot of time. Yeah, so I mean, one of the goals that we had here was to try to experiment with different ways to speed that process up. And one of the things we did here is, instead of starting from a simple model made out of an ellipsoid or maybe two connected ellipsoids, we decided to start with a similar shape model, which was 1996 HW1, which is also a bilobed asteroid. It's pretty strongly bifurcated, so it has these two globes connected by a neck, which is what we initially saw from the radar images of Midas.
Okay.
Even though that this model isn't going to be a perfect model for Midas, it at least allows us to get closer to our endpoint. So hopefully, any of the changes that we need to make are going to be smaller, which shape can handle better. And if you go to figure 2, you can actually see this.
Okay. Ooh. Okay.
Yeah. So here with the on the left in the first column, we have the delay Doppler images. So this is the real data. And then in the second column, it's going to be the modeled delay Doppler image. And then the third column, it's going to be like looking straight on at the modeled asteroid. And in the top row, we have our starting asteroid. So this is HW1, which you can see they're shared. We've been able to, we were able to start with just saying, okay, let's take this asteroid that's different and just have it have the same dimensions, so then we can play around with it more from there. So you can see it's about the same width, and we see the two lobes, which we should be seeing. But you can see that it still looks like a pretty poor match for the data. You have one lobe going down and then up again, and this looks like should be a more smooth view of this asteroid. Where after we were further along in the modeling process, we were able to get this modeled delay Doppler image to look more like the real image, which is great. That's the goal when we're modeling. We want to try to match the data.
Right.
But this just shows that we were able to go from one shape model and create a new asteroid out of that. And we do think that it was a lot faster to do it this way than to start with more of a simpler model.
Okay.
Another thing we did to kind of skip some of the shape not handling large shifts well is we actually used a software called Blender, which is usually used for computer graphics animation.
Right.
And also Microsoft Excel to make some larger shifts in the shape overall.
Okay.
So one of the first things we did with switching from our starting asteroid to a more Midas-like asteroid, if you go down to, I think, figure 3 and 4.
Okay. Figure 3. Ooh, there we go. Let's try.
Yeah, so figure 3. So HW1 was really strongly bifurcated. So one lobe was a lot larger than the other. which isn't something we necessarily see in mice. So what we had to do was apply a linear shift to all the vertices to be able to shift this neck more towards the center, which is what you see in figure A. This is what we started with HW1. And then B is shifting it to more of Midas-like proportions for the lobes. Which, yeah, it was great. Using Excel, we were able to use just a linear equation to apply a shift to multiple zones of the asteroid vertices, just so that we can shift it without putting vertices accidentally inside the model or ripping a hole in the model. And that just enabled us to make sure everything stayed continuous. Where then if you go to figure 4, one of the other things we had to change is we started out with a neck that was really steep. For some reason, the shape got stuck in this local minima of the chi-squared that had this really steep U-shaped neck that you see in A.
Yeah, right here.
And that's a really good example of something that shape would have a really hard time fixing, because you have to move this neck up quite a ways. So what we would do in this case is we would use Blender, and I would physically take all of the vertices and pull them up myself. So where it's closer. And I'm not, if you can see in B, I'm not trying to recreate the data specifically, because I'm not going to trust my eye to do that. I just want to get it close enough where the software can do that in a way that's like more statistically reliable. But it's just a lot easier to go to start at B than to start at A.
Exactly. Yep. I think that's great. You were able to go back and forth between Blender and Shape.
Yeah, and I should give a shout out. This was first done in Crowell et al. 2017, and they had a really successful time using Blender and were able to show its reliability. So if you're interested in that, check out that paper. It's great.
We put a link to it in the description below the video.
Yeah. If you can keep going, there are a couple other things that you have to deal with when you're shape modeling. So yes, we're looking for getting the shape correct, but we're also want to figure out the direction that the rotational axis is pointing. And because of that north-south ambiguity that I was talking about earlier with radar images, we don't know what's up and what's down just by looking at the image. We have to model that. And so we have to try to figure out, using a combination of the radar images and the light curves. This is really where the light curves come in handy, because we have so many more light curve observations. Whether the data is saying that this axis is pointing up or the axis is pointing down. And so we model both of these. We can't just assume that the northern pole direction is going to be better than the southern pole direction. we have to test this. So without biasing the model at all, we have 2 separate models running from the start. We have a north bias model and a south bias model. So whenever we're running our floating vertex models, where we're saying where are all of the vertices going, and our direction and our models that are looking to try to find out this rotational axis direction, we keep those separate, north and south. So as you can see in this figure 4, this is an example view with a northern pole direction, and you can see that it fits the light curves pretty well. So this the dashed line is the model light curve, and then the points are the data. So that seems to be a pretty good fit. But then when you look down at the delayed Doppler images in frames C and D, it's a pretty poor fit. So
right. Oh, yes.
Where if we look at figure 6, we can see that it fits. It's a slightly worse fit for the light curves, but overall the shape is still there. And then if you look at the delayed Doppler images, it's a much better fit.
Much better. Yes.
Yeah. So you can see that we're in the other in figure 5, it was the asteroid is pointing completely the other way.
Right.
From what the data show. Here it looks more like the actual asteroid.
All right. We have shape recovery.
We have shape recovery. Well, if we go to figure 7, then you can see the whole shape.
Oh, this is the money shot.
This is our model that we present from all 6 different axis views. So we can see that it has those 2 lobes. and looks kind of almost flattened a little bit. This is something that we see in some asteroids. I think Cleopatra looks kind of bone shaped in a similar way.
Good. Very different.
But and in this image, if you see the yellow shading, that just indicates areas of higher uncertainty. So one of the sides of the asteroids we weren't able to see quite as well in delayed Doppler images. So they're less well constrained. But overall, we were able to see most of this asteroid in that higher detailed delayed Doppler imaging.
Yeah. Very nice.
Which is great. Yeah, especially since we've only gotten radar observations from one close encounter with Midas in 2018. So the next time that Midas is going to come close enough to get good radar observations will be in 2032.
Okay.
And what would be really great is if we had a radar capable telescope that could acquire new data. If that is the next, I would love a next gen Arecibo. I know a lot of the folks down there would as well. But if we don't have that, then bistatic observations with Goldstone and Green Bank Telescope in West Virginia would be great to acquire, or even monostatic observations with Goldstone. But it was hard to beat that giant dish that Arecibo had.
Yes, it was.
Yeah, it really did wonders for
Will.
Yes. Yeah, it was really critical for our ability to observe the near Earth asteroid population.
Indeed. Very nice.
Yeah, so those are the main figures from the paper. Okay. If you're interested, we did some more detailed modeling about the gravitational environment of Midas, which is something that models are really useful for, especially when you have an oddly shaped asteroid that you can't just approximate with a sphere.
Oh, right.
Yes, this is very clearly not spherical. But we were also able to use the delayed Doppler image to refine the astrometry. So we've reduced the uncertainties of where Midas is in its orbit. And yeah. Very nice.
Very nice. I would say this is a pretty successful REU project.
Yes, it kind of kept growing and growing after the REU ended, and it was a really great experience.
Are most of the co-authors here, did they participate in that?
So I would say so Sean Marshall, who's the second author on this paper, was my REU advisor.
Oh, Sean.
And then Flaviani Venditti and where is her name? Oh, Anne Verkey, she's on the second line. Were also part of the Arecibo Planetary Radar crew. Okay. And then everyone else on here either provided unpublished light curves, of which there were many, and also may have helped with calculations. Shantanu Naidu did all of the gravitational environment modeling. Lance Benner helped with some density calculations, and Lance and Marina both provided great comments on this manuscript. So cool. It ended up being going from a really small team of mainly me, Sean, Flaviani, and Anne, and it ended up growing to this much larger project. We even extended all the way to an observatory in Slovakia. Mara Kusarik provided some light curves later on in our shape modeling that we didn't even know existed, and helped provide sort of an independent check on our model, as well as provide further evidence to rule out that northern pole position. It was a fun adventure. And we ended up finding out that Midas is one of the largest potentially hazardous asteroids out there.
NEO.
That's kind of exciting.
Yeah, so you touched a little bit there at the end, and I just want to encourage you to go a little farther there, maybe. Yeah. Where do we go in the future over, let's say, the next 2 to 5 years? Do we have to wait for the next REU project of Sean's, or are there additional shape model calculations that could be done? Is already data in the pipeline for another round of observation constrainings on the shape and so on? So just kind of where do we go over the next couple of years?
Yeah, so there's a whole group of people that are working on developing shape models for other asteroids, and we have a lot of legacy data, legacy observations of other asteroids that would be great to develop more shape models of. It seems like there's a lot more asteroids out there to model than there are people to model them. But also there's some work being done, and I know Sean's working on this, and so are some other people almost definitely, ways to improve our ability to model these asteroid shapes. So one thing that's pretty difficult to model is finding that direction of the rotational axis.
Mhm.
And this is difficult because shape changes one parameter at a time. So if it changes just the latitude of the pole direction, it's automatically going to be a worse model because you need to change both the latitude and longitude simultaneously.
Yeah,
So what we've done so far to combat this is do a large grid search, which I describe in the paper,
Mhm.
of searching a wide range of different pole positions, and then narrowing down when we find some that are better than others. But I think what Sean's doing is trying to find a way to use more like Bayesian statistics or maybe some Monte Carlo simulations to try to automate this process a little bit more and speed it up.
Mhm.
So that would be great. That would definitely speed up the shape modeling process a lot if we were able to speed up that specific part of the process.
Very cool. Well, I look forward to seeing those over the next couple of years. That will be
Me too.
great. So Riley, I want to thank you so much for taking the time and walking us through your very lovely article.
Yeah, thank you.
And that'll do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye-bye.